the Gauss's law. The Gauss's law means that the area integral of the electric field over any closed surface is equal to the net charge enclosed in the surface divided by the permittivity of space. So as is shown in the equation above, the E means the electric field turns at a specific point, and it is a vector. And the dA here means kind of special because although it stands for a very small piece of area, it is a vector, and the direction of the vector is perpendicular to that kind of small area. The Q here is the charge enclosed by that surface. Again, the numerical sum. And the epsilon zero means the permittivity of space, which is a constant. This might seem a little bit weird at the first time, but it is reasonable. So on the left, the E times dA is like the electric field penetrated into that surface we created. And this value is only connected to the charge enclosed by that surface. So it doesn't matter how many charge we have outside that closed surface we created. The E times dA, the integral, will always be the same. And we called the integral of E times dA on the left of the equation the electric flux. So note that there is a dot product between the vectors E and dA. So when E and dA are of the same direction, the cosine of 0 degree or 180 degree is equal to 1. So the dot product is just equal to A times B, or E times dA. The idea of flux might seem new, but some of you might already learned it when studying the Bernoulli equation. So for incompressible liquid, on the left, the area, cross-section area, A1 times the speed that water goes through that area is equal to A2, which is on the right, times the V2, the speed of the water as it went through area 2. So A1 times V1 is equal to A2 times V2. This is really similar to the idea of electric flux because it is again a kind of like a speed or something times the area. And for liquid, it could be easily proved true if we times a t on both sides of this equation. So now, if we add time, A1 V1 times t now means the volume of water flows through that cross-section in that given time t. While for electric flux, it's not that easy to prove. So let's use a special example to kind of gain some intuitive or kind of prove this idea. We have talked about it that for a given charge Q, the area integral of the electric field is constant, so no matter what closed surface we choose. And in this special case, the charge Q is put right in the center of the sphere, and the radius of the sphere is r. So now let's try to calculate the integral of vector E times dA. So since the Q is in the middle of that surface, and the Gaussian sphere we choose is a right sphere, so the direction of the electric field on the surface is always the same as the dA, which is perpendicular to the surface. And since the electric field is equal to k small q over r squared, and r is constant on the surface of the sphere, so E here is constant. So we could put it out of the integral sign. So now we get E times the area integral, which is kq over r squared times 4 pi r squared. 4 pi r squared is the surface area of that sphere. And after some numerical transformations, delta k is equal to 1 over 4 pi epsilon 0. The final thing we got is the q, which is in the center of the sphere, over epsilon 0. And this result matches the Gauss's law. So what we've just done is just like a proof of Gauss's law in some special cases. So when do we normally use Gauss's law? The answer is when the electric field E is constant throughout the Gaussian surface we choose. So therefore, when we choose the Gaussian surface, we should make it as symmetric as we can. So as an example, in this case, we are going to calculate the electric field strength of an infinitely large charged plate. So we assume that the plane is infinitely large and the charge is distributed evenly throughout the plane. Therefore, all the electric field lines are perpendicular to the plane. So in this case, we are going to build a cylindrical Gaussian surface with radial r, and it just cuts through that surface and enclose a circle region which have some charge. And we look back to the equation of Gauss's law, which is the closed integral of E times dA is equal to the Q enclosed over epsilon 0, which is permittivity. The first thing we are going to do is to simplify the closed loop integral on the left. So because the area integral should include all surfaces of the cylinder, and this electric field is perpendicular to the plane and parallel to the lateral surface of the cylinder. So the dot product of E times dA is always 0 for the lateral surface because cosine of 90 degrees is equal to 0. While for the bottom and the top of the cylinder, the electric field and dA are parallel. So the closed loop integral of E times dA here is just E times A, the area, because the electric field is constant over that surface. So therefore, the left part of the Gauss's law could be simplified into pi r squared, which is the area, times E, the electric field strength, which is a constant, and cosine 0, which is 1. And because we have both top and bottom, we need to multiply this by 2. So finally, we got 2 pi r squared times E. And this is the closed loop integral of E times dA that the cylindrical Gaussian surface we chose. So after we simplified the left part, we are going to deal with the right part, which is relatively easy. So the Q enclosed by that cylindrical surface is just the little circle area of the plane inside the cylinder. And that area is equal to pi r squared. And there's another thing, the charge density of the plane, the sigma. And the unit of it is coulomb over meter squared. So we know that we've just multiplied that charge density with the area and we'll got the charge. So the charge inside or enclosed by the Gaussian surface, in this case, is equal to the sigma pi r squared coulomb. So now we are going to combine the result of step 1 and step 2. 2 pi r squared times E is equal to sigma pi r squared over epsilon 0. So as we could see that the r squared here could cancel each other, and we finally figure out that the electric field is equal to sigma over 2 epsilon 0. There's something interesting in this case. The first is that no matter what is the radius of the Gaussian surface we chose, the result will always be the same because the r squared will cancel each other. And this is intuitive because the different way we try to calculate the electric field will always have the same answers for the same object we are measuring, and in this case the infinitely large plane. And another thing is that the height of the cylinder of Gaussian surface we chose also did not matter. And that is because, firstly, for the lateral surface, the closed loop integral of E times dA is equal to 0, so the area of lateral surface does not matter. And the second, which is more important, is that as we have assumed, for an infinitely large plane, the electric field strength do not change with the distance from that plane. It is always a constant E. So that's what make our cylindrical Gaussian surface possible to solve for the electric field of that plane. Another example of the uses of Gauss's law will be calculating the electric field inside a plate capacitor. The first thing we are going to notice is that the electric field only exists inside the plate. So outside the plate, we assume that there is zero electric field. And in this case, we will choose the same Gaussian surface as we did for the infinitely large plane. And we will put that Gaussian surface to the bottom plate, and it will not touch the top plate. It is quite obvious that the charge enclosed by the Gaussian surface in this case could be represented by the same equations in the infinitely large plane example. But since it's different when we try to calculate the closed loop integral. For the infinitely large plane, we have electric field strength in both bottom and top of the cylindrical Gaussian surface we chose. But in this case, because there is no electric field outside the capacitor, and the total area is just half of those in the former example of infinitely large plane. Well, however, those on the right are the same, while the left has a half area. To make the equation balanced, the electric field should be doubled and equal to sigma over epsilon 0. And this is also intuitive because now we have two plates. For the same charge density, now we have not only the electric field produced by the bottom plate, but also the top plate, and the directions are the same. So it is easy to remember that now we have 2 times the electric field strength than that of the infinitely large plate. The second example of Gauss's law will be calculating the electric field around an infinitely long rod, which is charged. So now the Gaussian surface we are going to build is a cylindrical surface with radius r and centered at the rod, all the way around the rod. So as is shown in the graph below, in the view of cross-section, in any place, the electric field is always perpendicular to the surface, which is parallel to any dAs. The electric field strength is also equal on the surface because of symmetry. So let's continue using the Gauss's law, which is the integral of E times dA is equal to Q enclosed over epsilon 0. And now the linear charge density of the rod is lambda, which have a unit of coulomb per meter. So again, it is obvious that the lambda times a certain length we will get the charge. So because the rod is infinitely large, the Gaussian surface we built, or the cylinder, should always be infinitely large, and we assume that it learns L. For the left part of the Gauss's equation, we could find that the electric field is again constant all over the surface, so we could put it out of the integral sign and left the integral of area. So finally we got E, the electric field strength, times 2 pi r times L. The 2 pi r L here is like the lateral surface of the cylinder, which is penetrated by the electric field. You might ask, why don't we conclude the bottom and the top circle of that cylinder? The electric field strength times dA, the area, is always equal to 0 for the top and bottom part, because the electric field strength is parallel to the area and perpendicular to the dA, so the dot product will be 0. For the right part of this equation, Q over epsilon 0, the Q, as we mentioned, is the lambda times L. So, and we put these stuff together, E2 pi r L is equal to lambda L over epsilon 0. And we again found that the length of the cylinder we choose does not matter, and they will cancel each other. However, this time, the radius of the cylinder matters, as is shown in the final result that the electric field is equal to lambda over 2 pi r epsilon 0. The electric field is related to 1 over r. So when the r is infinitely small, the electric field will be infinitely large. And when the r is really, really big, the electric field will be very small. So this means that the closer we are to the rod, the stronger electric field we are going to measure. And this is also intuitive. And also there's a graph plotting the R and the E electric field in the right down corner. And you can see it again that as R is approaching 0, the electric field becomes infinitely large. So let's do an exercise now. It might be a little bit difficult. And it is to find the electric field and potential on the axis of a charged circular wire. And again, we have a lambda for the linear charge density of the wire. On the left, as is shown in the cross section, we can see that the electric field is going out of the cross section. So first, let's deal with the electric field. So because the electric field at point A, which is on the axis, is generated by the whole circular wire, we need to divide the length into many small dLs. So because Q is equal to lambda times L, dQ is lambda times dL. For the electric field is equal to KQ over R squared. dE is equal to K dQ over R squared, which is K lambda dL over R squared. This is just some numerical transformations. And we need to notice that the vector E, the electric field, from opposite sides of the wire will cancel each other in horizontal directions, as is shown in the graph on the right. The contribution of area dE to the electric field overall will be dE times cosine theta. So repeat the result that we got on the last slide. The dE is equal to K dQ over R squared, and it's equal to K lambda dL over R squared. And area dE's contribution to the overall electric field is cosine theta times K lambda dL over R squared. So to get the electric field, we need to integral them together. So because For a given point, the cosine theta, the k, the lambda, and the r squared are all constants. So we could put them out of the integral sign, and the only thing in it is the dl. And since it is a circular wire, the integral of dl should be equal to 2 pi r. So now we got 2 pi r times cosine theta k lambda over r squared. Well, since 2 pi r lambda is the total charge of Q, we could further simplify this result to be the electric field is cosine theta kq over r squared. The Q here is the overall charge in the wire. So now let's deal with a harder part, which is the potential on the axis of the circular wire. Now we are going to calculate the potential, electric potential at point P. And as is shown in the picture on the left, point P have a distance r from the circular wire and a distance z from the center of the wire. And again, we need to divide this wire into many small parts, dl. And because dl times lambda is equal to dq, and v, the potential, is equal to kq over r, we'll easily get dv, which is the potential at point P generated by only a small part of the wire. It is equal to k lambda dl, which is an infinitesimally small part of the wire, over r. So now we again integral this dv to get the overall voltage or the potential. And again, since the k, lambda, and r are all constants, we could put them out of the integral sign, and we finally got 2 pi r prime, which is the circumference of that wire, times k lambda over r. And to further simplify this equation, the r squared, small r squared, is equal to the big R squared plus z squared. This is a right triangle. The final result of the potential along the axis of the wire will be 2 pi r prime k lambda over the square root of r prime squared plus z squared. This is the final answer.